Okay, so the second part of our today topic is going to be about the bolt screws. Again, we're going to go briefly about the theory and design. If you need to read more about that, you can go to the other references or you can check the textbook. In general, the power screw is different from the bolt screw is that the bolt screw doesn't have a direct contact between the nut and the thread. So it's going to be something like a ball sitting in the middle. So that's how it's going to work. You can see that these balls are going to be rolled between the thread and the nut, and thus it's going to work mainly like a bearing, and it's going to have more efficiency according to that. Um, that's an advantage and disadvantage difference from the power screw, but every one of them have a specific application. So you can see that in here we have a single set of the ball. We can actually have a different type which can go with the double. So that's what we call in general the external ball return system. This returning system is going to take the balls and put them back at the beginning and then thus going to be started rolling. So it's kind of like when you read in history about how they built the pyramids, for example, they were mainly roll them. So same thing is actually happening here. The balls are going to roll the sh- the whole knot over the thread or the bolt screw without having a direct contact with them. Thus, the load and the torque is going to be less than what we had earlier. So the basic action, same as the power screw as previously described, but between the screw and thread and the mating nuts, the rolling balls will minimize the friction. Less friction means we're going to have better efficiency because the losses is going to be less. That's it. So you can see actually the comment before we can go further that the bolt screw, you can see that the cut in that case thread is going to be something like a curvature because or half circular because we have the bolts need to be running through this gap. The nut itself is going to have the return tube, which is going to take the bolts and send it back to the beginning as they're going to reach the end. The bolt screw by providing the seal bolts between the screw shaft and the nut, and the bolts rolls in the groove, and thus we're going to have a change to the rolling contact from sliding contacts to reduce the friction. So a description of the bolt screw in general, the bearings balls circulate in a hardened steel races formed by the concave helical grooves in the screw and the nut. All the reactive loads between the screw and the nuts are going to be carried by the bearings balls, which provide the only physical contact between these members. As the screws and the nuts rotate relative to each other, the bearings balls are going to be derivated from one end and are going to be carried out by the ball guides return tubes to the opposite ends of the ball nuts. Now, we're coming to the description about the ball screws, the life relationship. So the load-life relationship is going to be very important when transmitting a load. The ball screws experience stresses similar to those to the ball bearings. The load is going to be transferred from the screw to the balls and from the balls to the nut, from a nut to the driving device. So this will be the steps. So again, the screw head's load is going to transfer them to the balls. The balls is going to take them to the nuts, and the nuts will take it to the driver, to the driving device. The contact stresses between the balls and the races in which they are going to be rolled causes a fatigue failure. Remember the fatigue failure term, and this will be indicated by the pittings of the balls or races. And that's similar to the example I show you in one of the bearings that we had in the class during the bearing session. So this relationship between the bearing load and life can be actually described in the figure 17.8 for the ball screw performance. We got that, of course, from the mod textbook, and this is chapter 17. So it's similar to the ball bearings, as you remember, from the chapter 14. So here we have the load, and here we have here the trouble life. Okay, so once again, the equation is going to be used at the life 2 to life 1, which is the design life here, and that's the standard design. It's going to be equal to the load 1 to the load 2 up to power 3. And remember, it was 3 for the ball bearings, 3.33 for the roller bearing. Now we come to the other description for this chart. Load here, trouble life here. You should know one of them to know the other. Here we're going to have the screw design data for the threads. Nominal diameters is going to be described by these different lines. The threads per inch is going to be also given for the standard types of the diameters, and the lead value, which is how much inch we are going to move per one rotation. So you will see now how we're going to use this one. For example, I have the trouble life for my design. Oh, I have the load. Again, to make the intersection with one of these lines, then I will know what will be trouble life. Or, for example, if I get to know the load and the trouble life, I can find what will be the best diameter. And that's how we're going to use this one. The the other copy, actually, I got it for the metric version from the old copy of the book from 2010. Well, you can see that the only difference is going to be that the trouble life in millimeter, the load in kilonewton, and the diameters will be given in millimeters for the screw types. So it started from 9.5 millimeter diameter up to 76.2, which is 3 inches. So the application considerations for the power screw and the ball screws are: first, the critical speed. The proper application of the ball screws must take into account their vibration tendencies, practically when they're going to be operating at relatively high speed. So they cannot work in high speed. Multiple parts vibration. We have to remember that. So the screw will tend to vibrate or whirl about the axis, possibly reaching the dangerous amplitude, and then boom, it's going to be filled. So therefore, it is recommended that the operating speed of the screw is going to be always below 0.8 times of the critical speed. Okay, so we can continue from that. The value of the safety factor for the design is going to be anything within the range of 1.25 to 3. So the belt design will employ the short length, rigid fixed support, and larger diameter. An estimate of the critical speed that we need to work within the zero point 0.8 value of it is offered by the Roton Products Incorporation, saying that the critical speed is going to be equal to 4.76 multiplied by 10 up to power 6 multiplied by the DKS divided by the safety factor multiplied by the L square. In the SI unit, the equation will be changed to be 187.6 multiplied by 10 up to the power 3 multiplied by the DKS divided by the safety factor multiplied by the L square. Now, the D is the minor diameter of the screw in inch or millimeters. The KS is the end fixed factor because this can be fixed from one side or two sides, right? And we have the L is going to be a length between the supports in inches or millimeters, and the SF is the safety factor that we said is going to be a range between 1.25 up to 3. So you can see that the highest safety factor is the lower critical speed we're going to have. Okay, that's one of the things. The higher the diameter is, the higher critical speed is going to be. If I get to fix it from one side, I'm going to have actually better support, and thus we're going to have higher critical speed can be operated with. If I get to have longer the length of the between the supports, I get to have lower value for the critical speed. So that's how we read this equation. So the end fixed factor, the case, depend on the manner of the supporting the ends of the screw. Now the other consideration we have for the power screw and the ball screw is going to be the column buckling. So the ball screw that carry the axial compressive loads must be checked for the column buckling. Parameter is going to be the material of the screw, the end fixity, the diameter, and the length. Now, of course, you know what the buckling is, right? So it's going to be about, we're going to have a quite lengthy shaft. It will start to buckle due to the load, due to the material, and due to the diameter, and due to the length, and due to the fixity. If I get to fix it from one point, it's going to be better than fix it from one end. Multiple supports is going to be better, but we cannot do that because the nut should be moving from one end to the other. So we cannot make it as a multiple supports in the middle. So we continue with the column buckling calculation. The Euler formula for the long screw or the J.B. Johnson formula for the short screw. This can be found in chapter number 6. However, the factors are different from the column loading. So simply supported at each end by one bearing, the Ks is going to be 1. That's good. Fixed at each end by two bearings that prevent the rotation at the support, the Ks value will be increased to 4. The fixed at one end and simply supported at the other is going to have Ks value to be 2. If I'm going to have only fixed at one end and free on the other side, the Ks value will be dropped to 0.25. So we always try to prevent having the cantilever shape. This will make it very dangerous. Okay, so we always try to prevent it because the Ks value is going to be low, and thus the column buckling is going to be quite critical. The failure load also at critical speed is going to be low, and so on. So the efficiency of the bolt screw can be calculated by the equation that the efficiency is equal to the load multiplied by the length divided by 2 pi torque. The torque to drive the bolt screw can be derived from the equation where the efficiency that to be set to 90%, set by the way that the efficiency can go up to 99%. So the equation for the torque to raise the load is going to be equal to the load multiplied by the length divided by the 2 pi efficiency. Okay, and by simplifying, it's going to be 0.177 multiplied by the load multiplied by the length. So that will be the torque. Now, the other thing we have is the back driving. So it's not going to have the self-locking as what we had in the case of the power screw. Doesn't have self-locking because of the low friction. So always the ball will keep rolling and thus the load will be dropped down if we are not going to be supported by a certain torque to hold the nut. So the back driving torque using the applied load to on the nut drive screw, and this will be equal to 0.143 FL. So remember that. Now, the torque to move the screw up is going to be 0.177 FL. The load to keep it in position is going to be 0.143 FL. We're going to use only these simple equations to find the value for the torques in both scenarios. And of course, if I know the torque, I can find the power. If I know the omega, you have to remember that. So we'll start with the first example, which is going to be about the torque, the power law, and the life of the ball screw. So we need to select a suitable ball screws for the application described in the example, problem 71. You remember the one that have the two screws on the side with the load of 134. I don't remember the number. Anyway, I can see it here. Anyway, yep, the load was divided between two screws, and we collected a power screw earlier, and now we're going to use a ball screw for that. So the hitch must be left for 15 inches to open it 8 times per day, and then must be closed. The design life is 10 years, and the lifting and lowering is going to be completed in no more than 12 seconds. So now what we know is first that left it for 15 inches every day, eight times a day. So 8 times 15 is going to be how many times we're going to have it per day. Let's say we're going to have 5 days a week for 12 months, for 10 years. We'll know what will be the total distance that ball screw is going to pass, and this will be the total service life. Also, we know the load, which is the I don't remember exactly how much it was, but this load is going to be divided by 2, and we can find actually the load, we can know the life, then we can find what will be diameter of the screw. Now, also this distance should be done in no more than 12 seconds. Then this will give me what will be the velocity. And then from the velocity, we'll be able to calculate what will be the omega, and we can find the power. So what's required from us here to remind the screw selected? Compute the torque to turn the screw and the power required and the actual expected life. So the solution will start first according to the figure 17.8. Data required to select the screw are going to be the load and the travel of the nuts on the screw over the desired life. So the load was, 110. So 55.6 kilonewton on each screw. Travel life to be calculated as. So we said 15 inches, which is 381 millimeter for every stroke. For 2 stroke, up and down, for 8 times a day, for 365 days per year for 10 years. Okay, and we're going to find that the total distance that the screw expected to travel is going to be 222.5 multiplied by 10 up to 5 millimeters. Now, simply from the figure 17.8, we can find that the 2 inches or the 50.8 millimeter screw with 2 threads per inches, and the lead of 0.5 inches or 12.7 millimeter is going to be the satisfactory one. So let's go back to the diagram and try to get these parameters and find it together. So 55.6 kilonewton, 222.5 millimeter multiplied by 10 to the power 5. So let's travel back to this scenario. Okay, so here we are with the load. Okay, so let me get my pen and let's start to sketch something here. 55.6, so this is 44.8. And then jump to 10 times here. So this will tell me that times 10 times 10 each time. So I need to be within this range. Okay, I don't want to go too much. And here we have 222.5 multiplied by 10 up to power 5. So this is 10 up to power 5. This is 100, 200, 222. And then we're going to do the intersection between both. It should be standing somewhere here. Okay, so now we come to the diameter of, well, hopefully I'm doing the correct thing. Wait a second. That travel time in millimeters. Yeah, this should be the correct one. So we're talking about something like 38.1. We can use this one. Thread per millimeter is going to be 2, and the lead distance is going to be 12.7. So let me check if I actually collected the same parameters. I choose the one above. 2 inches or 50.8 millimeter. Screw with 2 threads per inches, and the lead is going to be 12.7. Well, for me, I think that the 38 should be enough. Anyways, the torque now can be calculated by multiplying the 0.177 multiplied by the load multiplied by the length. And we know that the length is 12.7, okay, the L. The F is the 55.6, and the 0.177 is a constant. And thus we will find that the torque is going to be equal to 125 Newton meter. Now we can calculate from that velocity that we have already, we can calculate what will be the omega. So one revolution is going to give me 12.7 millimeter distance. We need to move for 381 millimeters in 12 seconds only. And thus we can find that the omega in that case is going to be 15.7 radian per second. Now I have the torque, I have the omega, just multiply them both. We're going to get that the power is going to be equal to the 125 Newton meter multiplied by 15.7, and this will give me 1.96 kilowatt. So the power required using this ball screw is going to be quite smaller than that we used in the power screw, which was 6.42 kilowatt shown in the example 17.2 that we covered earlier. So for the tutorial, we're going to have a similar example. We have the ball screw